Hello everybody, this is Vas from At Home Tuition. In this video we are going to learn how to find the highest common factors using Euclid's division theorem. So in Euclid's division algorithm, actually what we do is it's a technique we use to find the HCF or GCF, whatever you call it, of two numbers, okay? If it is a smaller number, we normally know how to do it. We can do it in easiest way. When the number becomes too big, then this Euclid's division algorithm proves to be very easy to us. And here normally we take only the positive integers. We find the HCF of positive integers. Though Euclid's division algorithm is for positive integers, it could be extended for even other numbers, even negative numbers, provided your b is not equal to 0. Except 0, you can find HCF for any numbers. Okay. So what we normally do is we try to represent the numbers given in this form. A equals BQ plus R. Okay. So where your A and B are the numbers given, you take A, the bigger number, as A and the smaller number as B, and Q is the quotient and R is the remainder. Okay. We try to put the numbers in this form. So I can show that with an example so that you can understand it more better. So here you are asked to find the HCF of 867 and 255 using the Euclid's division algorithm. So as I said, we are going to put this in this form. Okay, the bigger number you take it as A equals B. B is the smaller number. Normally we take that as smaller number, and your Q is the quotient plus R. R is the remainder. Okay. So here in these two numbers, your bigger number is 867, right? So 867 is equal to, you have to put the smaller number, which is 255 times Q. So the Q, you can take it any number, like just see how many times it goes in 867, right? So that would be 3 times. So, and the remainder here you would get 102. Okay. So you can write this 867 as 255 times 3 plus 102, where your 255 is a smaller number given here, and this 3 is the quotient you have found out, and 102 is your remainder. Okay. Now in the next step, what we normally do is you just move this 255 to this side, or left side of the equal to side, and this remainder you bring it to this portion. Okay, this side. So we keep doing this. So in the next step, what happens? Here you would have 255 equals, and 102 is moved to here, and let's see how many times it goes. Like it would be 2 times, right? Because 2 times 102 is 204, so the remainder left out would be 51 here, right? So write the remainder here. Next step, bring the 102 to this side, and this 102 moves to this position, to the left side of the equal to side, and this 51 should come here, right? So what happens? This time it is 51 times 2. I take it as 2, and you don't have a remainder here because 51 times 2 is 102, so your remainder is 0. Now your problem is over. You stop here. When you get 0, you stop the problem, and just the previous remainder would be your HCF. This remainder here would be your HCF. So therefore the HCF is 51 for these two numbers. Okay. So simple, right? However big the number is, you can do it, use the Euclid's division algorithm and get the answer within minutes without much thinking or calculation. Okay. So your HCF is this. Now I have taken even more bigger numbers, and I'll just do that once again so that you get a clear picture of it. So this is 7,398. The bigger number I put it on the left side, and I take the smaller number here, 2,877 times 2. I can take it as 2, and your remainder would be like 1644. Okay, just do the calculation. This is what you get. Now move this 2,877 to this side. 2,877 equals, and the remainder is moved here, so that is 1644 times, again this I cannot make it 2 because if I make it 2 it goes beyond 3000, so I just take it as your quotient is 1, and now the remainder would be 1233. Okay, now again bring the 1644 to this side, and here it is 1233 times, this could be taken only once, right? And your remainder here is 411, right? Good. Now take this 1233 this side to your right, left, and then bring down this 411 here. So I think this could be done 3 times, right? So that is exactly 1233 when I multiply 411 with 3. So I don't have any remainder. So my remainder is 0, and there the problem ends. Okay. So what happens? The previous remainder will be your answer. The HCF is 411. Okay. Here the HCF is 411. That's all. It is as simple as that. So if you get direct problems like this, maybe you can do it easily. Sometimes they may ask you to prove few things, okay? Like, just take this example. Here they say, show that any positive odd integer is in the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, okay? Where q is some integer. Okay. So now, since we don't have the numbers as such, we take the numbers as a and b. Okay. Let the variable a be the positive integer. Okay. Positive integer. And I take the b as, here since it is the coefficient of q is 6, right? My b would be 6, right? It is given here. Now just listen. Since it is b is 6, your remainder will be something less than, your remainder should be something less than 6, right? So that is, it could be, it is all positive numbers we are talking about. So it would be your remainder can be 0, 1, 2, 3, 4 or 5. It can be any one of these, okay? It cannot be 6 because when it becomes 6, it is again here, this will change, right? So the remainder can take up the value 0 to 5 only. Now let's prove. We are not asked to do all the numbers, like, say for instance, I'll do with 0, first number 0. When the remainder is 0, what happens? Your a equals 6q, okay? 6q plus the remainder is 0 here, right? So this 6q I can write it as 2 times 3q plus 0. So here this is an even number, because whatever number you get here within the brackets, when you multiply by 2, it becomes a even integer, positive integer, okay? So even integer it is. So we are not bothered about the even ones. They just ask you, I just gave you this as an example. Now we need to prove only these 6x plus 1, 6x plus 3, 6x plus 5. Okay. So let me write first one. My A equals 6q plus 1. Okay. So this I can write 6q, I can write it as multiples of 2, right? So that would be 2 times 3q plus 1. I said when you multiply this bracket with a 2, it becomes an even number, right? And when an even number is added with 1, when you add 1 to an even number, it becomes an odd integer. Understood? So this is an odd integer here. Now, let us go on to the next one. Second one they said is 6q plus 3. So I have taken it as 6q plus 3. This could be written as 6q plus this 3, I can split it as 2 plus 1. Okay. So out of these I take 2, the common factor out. Okay. 2 out. So this will be 3q plus 1, right? Plus you have this one left. Okay. So that one I have written here. So again what happens here? When you multiply this bracket with 2, it becomes an odd even number, and this even number to this, if you add 1, it becomes an odd integer. Okay. So that becomes an odd number again. Got it? Now, the next one they was to prove is 6q plus 5. So it is just the same. Just do the same. Try to split the 5 as 4 plus 1. Okay. So what happens here? It is 6q plus 4 plus 1. Now this, out of this I take the 2 out because I have to show that that is an even number. Okay. So this will be again 3q plus 2, right? Plus 2. Whatever be within the brackets, when you multiply, it becomes an multiply with 2, it becomes an even number, and you are left with this plus 1 here. So when you add this 1 to an even number, what happens? This again you have got it as odd numbers. Okay, odd number. So now you see that whether you take 6q plus 1 or 6q plus 3 or 6q plus 5, they are not exactly divisible by 2 because you are adding this by 1, right, every time. So it becomes an odd number. Okay. So these expressions of numbers are odd. Any odd integer can be expressed. So you have proved that any odd integer will be in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. So your 6q plus 1, 6q plus 3 and 6q plus 5 are not exactly divisible by 2. I tell you why. Because here when you multiply by 2 and then add 1 to it, it becomes an odd number, right? For example, you can take any even number. Say for instance, if I take 10, add 1 to it, it becomes 11, which is an odd number, right? So any number likewise, if you check, it becomes an odd number. So since here you are adding 1 to all these even digits, it becomes an odd number. Okay. Hence these expressions of numbers are odd, and that's it. You have proved. I hope you understood how the Euclids division algorithm works. See you in the next class. Bye.